Welcome to our third video on robot controllers. In order for you to understand the content, it is important that you have previously watched the video overview of robot controllers and the video core knowledge about robot controller development. We will look at cascaded kinematic control in this video and then also learn about control using the dynamic model of the robot. To understand the cascaded kinematic controller, we start with the kinematic controller as we learned it in the last video. We have seen that with the kinematic controller we calculate the positioning acceleration with the PD controller algorithm, which we then multiply with the mass matrix to obtain the positioning force. We now need to reformulate the algorithm so that we get two superimposed control loops. Using a proportional controller with the control parameter kV tilde, we calculate the position acceleration from the detected velocity error E dot c. The input variable E dot c is essentially the velocity error, which is the target velocity minus the actual velocity. To this is added a proportional controller for the position with the control parameter Kp tilde, which supplies a correction value key.cp in the presence of a position error E. But exactly which controller parameters do we have to choose? The position controller is Kp tilde times E. The velocity controller is Kv tilde multiplied by the sum of the velocity error and the control speed of the position controller. We insert q.cp from the first equation into the second and multiply out. We compare the result with the kinematic controller. We see that kv tilde is identical to kd and is 2 times d times omega. Kp tilde is kp divided by kd and thus omega divided by 2d. We can now insert the control parameters into the diagram to get a better overview of the cascaded kinematic controller. But why do we use a cascaded kinematic controller anyway when we achieve exactly the same effect as with the kinematic controller? By dividing the system into two cascaded control loops, we can intervene between them, for example by limiting the positioning speed of the position controller and thus prevent dangerous speeds. Or we can run the two controllers in different coordinate systems, or even on different microprocessors. If the system moves at a constant speed and has no speed and position error, the positioning acceleration is 0, so the speed remains constant. Only in the acceleration phase must the speed controller first have an error at the input, so that the corrective acceleration is initiated. If you want to avoid this, you can feed forward the setpoint acceleration. Unlike in this diagram, however, the target acceleration is normally taken from the path planner and not determined by the derivation. Let's look at what we can achieve in robot control with our knowledge of the dynamic behavior of the robot. For the first considerations, we use the diagram axis controller with additional speed values from the first control video as a starting point. If we want to build a system that has as little control error as possible, it is useful if we feed forward the entire dynamic system that we have modeled in the robot dynamics. For this we use the actual positions, actual velocities and target accelerations. But we could also use only the planned values if they are available. This is what we call the feed-forward algorithm, while we call the controller itself the feedback algorithm. It is nice that we are now using the dynamic equations to optimally feed-forward control the robot. But we still have the problem that the inertia of the robot changes during the movement, which affects the feedback control. In control engineering, we call this shifting of the poles. This can be prevented by introducing a kinematic controller and using the mass matrix that we learned about in the video on robot dynamics. With this, we have found the ideal control architecture for robots. We now want to combine the concept we found with our cascaded kinematic controller. For this purpose, we have to consider the dynamic equations of the robot. In a first step, we also illustrate the controlled system a little more precisely by adding the nonlinear terms and the gravitational term to the system model. We already take the mass matrix into account, which is why the shifting of the poles is already solved. Now we supplement the controller with the compensation for the nonlinear effects and the gravitational term. Then we also add the feed-forward term for the acceleration with the mass matrix. Because the mass matrix occurs twice in the controller, we see that we can save arithmetic operations by summing up the accelerations before multiplying by the mass matrix. Now we have found the cascaded kinematic controller with computed torque feed-forward based on the dynamic model of the robot. As a next step, watch the video about observers and learn about how to use them for sensor fusion in mobile robotics. For the implementation, we recommend the open source robotic framework EROS, which we also use in this course. You find it on eros.org or wiki.eros.org. All course materials are available on Moodle at online.robotics.ch. We are happy to answer your questions or suggestions in the forum on Moodle, or if you are not enrolled in the course, in the comments here.